For the most part, she's still.
Yeah, it's not seeing it.
Okay, welcome everyone. We just heard an ITC colloquium from the former ITC postdoc, Lorenzo, that left us in New York City and has been doing fantastic work since then, and he will speak about some more his work, to be or not to be, the origin of magnetic fields in the universe.
All right, so I'll start.
We still have more people to mention. And then we'll hear from Hyerin Show, that we'll talk about bridging scales. Where is Hyerin? Oh, great. From here and from Canada, bridging scales of black hole accretion and feedback in GRMHD. And then we'll hear from Franz Bauer, who came all the way from Chile. And we'll talk about the ALeRCE broker. What is ALeRCE?
It's ALeRCE.
ALeRCE. Okay. And you will
It's actually a
explain.
tree. It's the oldest tree in South America.
And then finally we'll hear from Daichi Hiramatsu from the CFA. We'll talk about the energetic interacting supernova,
Here we go.
supernova in complex circumstellar environment. Lorenzo, is everything good?
Yes, now everything works, just precise, perfect timing. Okay, so this is my catchy title, To Be or Not to Be, where B, of course, stands for magnetic field, the origin of magnetic fields in our universe. A less catchy title and more technically informative, how to generate magnetic fields in turbulent, collisionless plasmas. So the motivation here is to understand with an astrophysical mechanism the origin of magnetic fields in our universe. And the challenge is especially hard for cosmic voids. These are the most pristine regions of our universe. They are big, 10 to 100 megaparsec across. They're nearly empty. The particle density is as low as 1 proton per cubic meter, which means that the chance for collisions is very low. This system is fairly collisionless. This word will come back a few times, collisionless. And it's magnetized. We now have not only upper limits on the fact that there should be some magnetic fields there, but we also have lower limits thanks to recent Fermi GeV measurements or lack of measurements. The inference is that magnetic fields in cosmic voids should be at least as strong as 10 to the minus 15 Gauss on scales unconstrained but over megaparsec, maybe smaller than that, maybe larger than that. The scale spans a few orders of magnitude. But the strength seems to be relatively robust. So how do we make these magnetic fields in cosmic voids? And the hypothesis that I'm going to bring forward is that turbulence in a collisionless plasma can do it. So let's think about this thought experiment, the Gedanken experiment. Take a box of zero magnetic field, collisionless plasma, collision-free plasma. You stir it. This would mimic the gravitational effect of large-scale structure, galaxies, galaxy clusters. What happens? And if you were to do it in MHD, if you were to do this in MHD, nothing happens. This is the equation you would be solving. It will have an advection part, maybe a diffusive part, if you're allowing for resistivity. But if you plug B equals 0 on the right-hand side, you get the derivative is 0. B will always be 0. B will always be 0. That's nice as well. But the system is not properly described by MHD. MHD intrinsically assumes that the gas is collisional. And as I convinced you, cosmic voids are not in that collisional limit. So the most fundamental way of describing a collisionless system of charged particles is with this method, the so-called particle in cell method. It captures basically Lorentz force and Maxwell's equations interplay of charged particles with each other and with electromagnetic fields that they themselves generate. So we'll use this method to perform three-dimensional particle in cell simulations of turbulence in a collision-free, collisionless plasma. And my argument will go through 3 stages. First stage. So take 2 blobs. One is pink, the other one will appear here. It's going to be green. The pink blob is at rest without lack of generality. It has some temperature. The particles are isotropically oriented in this pink blob. Take the green blob. In its co-moving frame, the particles are still isotropically oriented, but they're moving down. This will mimic sort of like shear motion of turbulence. If you were to have strong collisions, whatever are the particles, all the particles in this green will remain in green, all the particles in pink will remain in pink. But this system is collision-free, collisionless. So at some later time, the pink blob will, let's say, assume that it retains its particles, but it will also have an influx of particles coming from the green blob, which are depicted in green here. And these particles will bring a bias towards velocities pointing down, because that's where the velocities, that's the bias that the velocities in the green blob initially had. So the distribution here, the particle properties here, have some degree of non-isotropy. You have a preferential directionality of your particles pointing down because of the quote-unquote pollution of the green particles on top of the pink blob. And plasmas now can exploit this free energy related to the particle anisotropy. And they do it by releasing some of that free energy into basic plasma instabilities. One of them is the so-called Weibull instability, and our esteemed chair of the ITC Luncheon is an expert of that. What these instabilities can do is to make magnetic field from scratch. It's a beautiful property of collisionless plasmas. If there is some free energy available, some of that free energy can be channeled into making magnetic fields from scratch. It's going to be stage 2, magnetogenesis. So fields are generated by the Weibull instability, that instability that feeds off the anisotropic particles. This is shown here. This will be a plot over time of the thermal energy, the bulk energy. It takes some time to get it going because you're starting to stir and initially there is no velocity. This is the magnetic energy. This growth, exponential growth, is what's associated with the Weibull instability. The Weibull instability typical spatial pattern is like this. It organizes into filaments of different sign magnetic and electric fields as well. All great. We have been able to magnetize a plasma that otherwise would not be magnetized, but the Weibull fields are small scales. The typical scale of this box is maybe like 100 to 1,000 of the fundamental scale of astrophysical plasmas. These scales of the Weibull filaments are small, and they're very weak. So you see that there are still few orders of magnitude away from the bulk energies, and from realistic systems, this would be even more of a separation of energy scales. So they're still not good enough. So what you do, you keep stirring the turbulence. And your seed fields will grow to much larger amplitude. The pink here is the window that I showed before of the previous plot. But you're extending now this steering to many, many more steering time, turnover, what we call turnover time of the turbulence. And the magnetic energy in the end goes up to about a factor of 2 away from the bulk energy. So you end up with magnetic fields that are nearly as strong as the turbulent kinetic energy. And they're on much larger scale. Compare this plot with what you had in your memory from the slide before. This is much bigger structure that we now have in the magnetic field. So this is already very promising. Let's quantify this a little bit more. This is the magnetic power spectrum. So how much power you have is a function of K. K is given in units of this fundamental scale of plasmas that is microscopic. Initially, the Weibull field is what's giving this bump. High K, small scales, and weak fields. The magnitude here is not that large. But then over time, as you keep stirring, it goes to larger amplitude and smaller scales. Sorry, larger scales, smaller K. So in the nonlinear saturated dynamo stage, this process that allows to take the seed fields twist them, fold them, increase the field strength as a result of that, eventually the peak of the magnetic spectrum is sitting at a wavelength that is just a factor of 10 smaller than the scale over which you're driving your turbulence. So you started from very small, very weak fields, you kept stirring, and then you get, with large scale, strong fields. I have one more slide to convince you that this is real. We're always limited by scale separation. The plasma scales are much, much smaller than the scale of cosmic voids. We are not able to reproduce this on the realistic scale separation, but we do the best that we can by varying the ratio of the box size or the scale over which the turbulence is being stirred and the plasma scale, an order of magnitude change. What are the common properties? The magnetic energy always gets to about half of the kinetic energy, of the turbulent kinetic energy. And with a larger and larger separation of scales, the peak of the magnetic spectrum shifts once measured in plasma scales leftward and leftward, such that it's always sitting at 0.1, at a wavelength that is 0.1 of the stirring scale. So I think the general conclusion is that if you're starting with zero magnetic field in your plasma, and the plasma is collisionless, as it should be in cosmic voids, then you're able to magnetize it with a strong and large-scale magnetic field. And this is my punchline. This work that had been done with Luca at Columbia and my student, Ryan Goland. Again, strong magnetic fields nearly in equipartition with the turbulent kinetic energy, and large scale, where large scale means just a factor of 10 smaller than the scale over which you're steering your turbulence. Now, I've cheated all along. I didn't mention this at the beginning, otherwise you would not listen to me. All of this has been done for an electron-positron plasma. Why that? Because that's what we can do. The simulations are incredibly expensive, the biggest particle in cell simulations that have ever been done. And in order to get enough separation between the turbulence steering scale and the plasma scales, we really needed to extremize everything we could. So we did it for a pair plasma. Next in line is a more realistic electron-ion plasma. I can discuss about differences that I expect and similarities that I'm convinced of. New GPU-accelerated peak codes that we have at Columbia can, at least for a reasonable mass ratio, address that problem. The surprising thing, at least from my perspective, is that we know very little about the properties of the turbulence in cosmic void. So in order to put this into a realistic cosmological context, you really want to know what are the properties of the turbulence there. And we're working with sort of like cosmological experts, of like simulator expert from the cosmological point of view, to address this question on a more like cosmological basis, and then put this underlying physics in there to hopefully find at least an alternative way to primordial fields for magnetizing the universe. Well, thank you. And as Javi said, I was here before. It's nice to see many familiar faces. It's nice to see that the ITC Luncheon is still a great place to meet and talk about science. Thank you.
So Lorenzo, there was another cheat that you didn't.
There was?
There was another cheat that you didn't mention.
Which one?
In the beginning, you showed this equation that you argued it does not produce any magnetic field, but we know of the Biermann battery. If you
Correct.
have a temperature that is not parallel
Perfect.
to density, then you can do that.
Perfect. Yes. So in reality, I mean, any process that here does not depend on a magnetic field, which should be called a battery, will make those magnetic fields. Now, the Biermann battery will be there as long as you have different masses. So it definitely is a competitor to the mechanism that I just described. Weibel makes small-scale fields strong. Biermann battery makes large-scale fields weaker. It will not show up in the electron-positron case. That's why I did not mention it. For our sort of limited study of electron-ion cases so far, they both occur. The Weibel takes over relatively quickly. Now, whether this will carry over to realistic scale separation, I'm not ready to say yet. But the two processes are seen concurrently. The Biermann is staying weak, and the population, the way to populate the field at large scales where Biermann initially grows is ultimately coming from the Weibel part. So the dynamo, I think, picks up from the Weibel.
Thank you. Questions from Ramesh?
So, Lorenzo, this is really great. you are making small scale fields from wide.
First, yeah.
And then somehow your dynamo, whatever, is pushing it up to larger scales. What kind of spectrum does it produce?
Yeah.
And where is most of the energy, large or small scales?
So this is the magnetic spectrum in the saturated, yeah, maybe this one also. The saturated spectrum in the saturated dynamo stage. So this dominant scale, the integral scale of the magnetic turbulence, is what I quoted as the 0.1 of the steering scale. This one, I mean, I'm not sure whether I would call it Kolmogorov. There is a prediction of dynamo even in MHD that the low energy or low K part of the magnetic spectrum should follow a different scaling. It's called Kazantsev scaling. Not really in the saturated dynamo stage, in the kinematic stage of the dynamo, so when the field is being brought up exponentially. So that's, I mean, if you want, this is how it looks like. It's a bell-type shape with a slope that is maybe K to the 1 here, so this will be K to the 2 once you multiply by an extra K factor, and then kind of Kolmogorov beyond the peak.
To me, it looks flat.
Yeah, I mean, for the range that we can do, it looks flat. I think there is better indication of the Kolmogorov range in the kinetic power spectrum of the turbulence. This is by itself a non-trivial statement because you don't really have viscosity here until you grow the magnetic field. So if you were to do this without magnetic fields, and the magnetic fields are kind of suppressed, then you only have motion at the steering scale. There is no hydroturbulence here. There is no such thing as hydroturbulence here. It's a collisionless plasma. So you would only have power here. But then you build this power because you're growing the magnetic field. And then the power that you build in this intermediate range looks like Kolmogorov.
So you're making a collisional through the magnetic.
Exactly. So that's a key point. Yes, the magnetic field makes the plasma effectively collisional, and it allows a dynamo, which is really a collisional MHD process, to operate at that point.
Yeah, please.
Yeah, so related to that point you were just making, you were talking about bridging to cosmological simulations. So in those simulations, unless I'm aware of one that doesn't, even in the void regions, they assume like hydrodynamics, right? So the approximation there is that's collisional. So how do you determine what you can glean from the turbulence in the void from something that doesn't assume what you have to?
Good question. So, so the scales where the magnetic turbulence will be most important, let's say higher than the peak, are likely to be collisionless. But at the very largest scale, they're nearly collisional. So I would trust the hydrodynamics of the cosmological part to understand what is the steering scale. I would not really trust too much of, like, if there is a hydroturbulent cascade, we measure the properties of the cascade. I think this will be true up to the K vector for which the gas should really be thought of as collisional in the usual Spitzer terms. Yeah.
Okay.
But it's a very rich field, actually. I mean, then you could criticize and say, but you have magnetic fields coming out of galaxies, polluting the cosmic voids. I think this is a completely fair criticism, and I would love to understand more of how constrained those models are. How well can we model pollution of cosmic voids by galaxy-produced and galaxy cluster-produced magnetic
Well,
fields?
this was calculated, but the filling fraction of the intergalactic field is small until recently. So if you go to redshift 1, there wasn't, I mean, there are outflows from HEN, but they don't fill much of the void. Any other comments? If not, let's
Right.
start Lorenzo
Okay.
again.
Oh. No? Yeah, there you go.
Hi, I'm Hyerin. Can you hear me well? Okay. I'm a fourth-year graduate student working with Ramesh Narayan, and today I'll be talking about bridging scales in black hole accretion and feedback in GRMHD simulations. Observationally, we have found that small-scale properties of the black hole and large-scale properties of the galaxies are correlated with each other. And here I'm showing one of these examples where the black hole mass and the stellar bulge masses are correlated. In order to, because these scales between the black hole and the galaxies are orders of magnitude different, there has to be some kind of two-way communication happening between scales in order to explain such correlation or black hole galaxy coevolution. And there are two simulation tools to study that. One is galaxy simulations with Newtonian gravity, where usually the best resolution is around 10 parsecs. And translating that to gravitational radius, or which is half the shorter radius, for M87's case, that corresponds to 3 × 10⁴ Rg. The other type of simulations is GRMHD simulations, usually focusing on the vicinity of the black hole. And because these are very computationally expensive, it usually only converges from the event horizon to maybe 100 Rg. So note that the length scales that these simulations cover have very little to no overlap at all, which makes it very challenging for us to understand how this communication happens. So then we can ask this question of why are we not doing just a huge simulation with the black hole and the galaxy self-consistently? This is because the time scale of the simulation would be determined by the smallest length scale by current conditions. However, the total runtime of the simulation would be determined by the length scale that we want the convergence up to. So if I imagine a simulation if I want a simulation converging from the event horizon scale to, say, Bondi radius, which is around 2 × 10⁵ Rg, that's going to take me more than 15 years to complete in Harvard 804 GPUs. And that's very impractical. Now, there has been several successful attempts to bridge these very disparate scales, and they have been very successful in tracking the inflow or accretion from large scale to the inner scales. And I've listed them here, and these include nested simulation methods as well. However, to the best of our knowledge, there has not been a simulation tracking the other important side of the communication, which is outflow or feedback. This motivated us to come up with a new method that we call multi-zone method, specifically for hot accretion flows case. We use a GRMHD code called Karma in order to do this, and the method is very similar to a V-cycle. So instead of trying to simulate the huge spherical grid going from the event horizon to galactic scales, what we would do is instead we would split them up into different annuli or zones, which are represented by different colors over there. And then the idea is to only simulate one active zone and fix everywhere else frozen. The idea is, so the first half of the schematics is very similar to the idea of nested simulations. The y-axis is showing the radius in logarithmic scales, and the x-axis is showing the runtime of the simulation. So similar to nested simulations, each zone would be initialized from the last output of the larger zone that's neighboring it. And this, the difference from the nested simulation would be, though, however, we are sliding this active zone not only inwards, but also outwards in order to capture both accretion and feedback at the same time. The other difference from the nested simulation is that we don't stop in just one V-cycle, but we actually repeat this V-cycle for multiple times until we reach a statistical steady state. And this movie is showing exactly that. So 2 black circles are indicating where the current active zone is. And you notice that only when it's an active zone, the simulation runs, and otherwise it's staying frozen. So this allows us to bridge scales. Instead of trying to apply this to realistic and complicated systems, we wanted to test it out in the simplest case possible, which is purely hydrodynamic Bondi accretion, where there's no black hole spin or gas rotation. This problem is specifically good because we know the relativistic analytic solution, so which we can compare our numerical results to. The left panel is showing the spherically average density as a function of radius in gravitational radius units, and also physical units in the upper x-axis. And the Bondi radius is around 2 times 10 to the 5, which I've indicated with a vertical gray line. The analytic solution is shown in a thick gray line, and our numerical results is shown in red line. They agree perfectly, very well, with a characteristic slope of r to the minus 3/2 inside the Bondi radius. And on the right panel, I'm showing the feedback efficiency parameter eta, which is, if it's a positive value, it means there is feedback coming from the black hole scales to galactic scales. And if it's a negative value, this means there's no feedback and there's only an advection of energy from larger to inner scales. The solid line means it's a positive value, dotted line means it's a negative value. So both analytic solutions and numerical solutions agree that there's no feedback, and the amount of energy being advected is around 10 to the minus 5 of accreted rest mass energy. This problem was fairly simple because the only direction of information is coming from large scale to small scales. However, the real challenge would be when we add strong magnetic fields onto the same problem, where it's going to make strong turbulence, and there will be also outflow on top of inflow. And our method should be able to capture both directions. Here I am showing our simulation snapshots for this MHD case, where each panel represents each zone or each annulus. And you can take a look at the scale bar to see what length scales each are associated with. Each panel's left half shows plasma beta parameter, which is basically gas pressure to magnetic pressure ratio. And right half of each panel shows the density with magnetic fields overplotted. In this specific snapshot, we have captured the moment of very strong outflow, which you can sort of see here by yellow blob. So it indicates that just by adding magnetic fields, the system has gotten a very highly energetic outflow. Here on the top panel, I've also plotted the accretion rate onto the black hole horizon as a function of time, where the accretion rate is in units of Bondi accretion rate, and time is in units of free fall time scale at Bondi radius, around 76 kiloyears. After a few TP, you can see that the accretion, so it's in black line. You can see that accretion rate fluctuates around a constant value of 5 times 10 to the minus 3 of Bondi accretion rate. And this amount of suppression is actually consistent with Sagittarius A star or M87's observations. We can repeat the same analysis as before, trying to look at time average radial profiles of the density and feedback efficiency. And the new addition is now black lines. And on the left panel, you can see that when we have strong magnetic fields, the density slope has changed to r to the minus 1, which is again also consistent with X-ray and EHD observations. And on the right panel, this is feedback efficiency, and the solid line indicates that it's a positive value. So by adding strong magnetic fields, now we have a feedback. And that amount of feedback is around 1% of accreted rest mass energy. And we were originally, when we first saw this, we were very surprised to find there is feedback because we didn't include any type of black hole spin or gas rotation. So here we report a minimum amount of black hole feedback in MHD. because when we add black hole spin, there will be a relativistic jet, or if there's a rotation of the gas, there will be a disk wind. So the feedback efficiency will only increase from here. I will end with the summary. So using our multi-zone method, we are now able to track both-way communication between the black hole and the galaxy. In the simple, purely hydrodynamic case, we find perfect agreement with analytic solutions, and we find no feedback. When we add strong magnetic fields, now the density has changed its slope, and the accretion rate has been suppressed, both of which are consistent with observations. And we find feedback even in the absence of black hole spin or gas rotation. In the future, we aim to run simulations more in realistic galactic environments, and also we're very excited to add black hole spin onto the simulation in order to get relativistic jets, and then we will be able to provide realistic subgrid prescriptions to cosmology simulations. So please stay tuned, and thank you so much.
That you tend to remember what was done 45 years ago. And I remember a paper in 1978, actually, that was part of a PhD thesis of Len Covey with Jerry Osraker. And there is a paper of the two of them, plus Tony Starr, who I guess is not in the room, but from 45 years ago. But they basically argue that there are cycles for an accreting black hole. You put a black hole in a Bondi setup, and they indeed talked about this feedback, but I guess you haven't seen that they work.
I don't think I didn't see their work.
How wrong did they get it back then? Because now obviously you have better simulations, but they did also a spherically symmetric calculation. That was the PhD thesis of Len Covey, who later became an observer.
I see. It's a simulation work with MHD?
In spherical symmetry, they try to solve it theoretically. Anyway, you might want to
I should look it up.
Just to illustrate what is new in terms of comparing to all the numerical codes. Go ahead.
I think this is just a framework for us to actually go into the jetted case. So
right. They did purely spherical.
I see.
Go ahead.
So I was wondering, in your plot where you show the snapshots, on what scale are you seeing this feedback energy being deposited? It looks like it's roughly around 10 to the 5.
Yeah. So
RG, so it's not really expanding out to the galaxy scale yet.
yeah, here in this work, we are finding that it's usually deposited around the Bondi radius. But we are expecting that if we actually have the black hole spin and if we actually have the relativistic jets, we hope to see this actually pushing through beyond the Bondi radius. But here in this work, we were finding that it's usually deposited around Bondi radius because we don't have any black hole spin.
Go ahead, Lorenzo.
I should probably read it from this plot, but so the initial field is like uniform vertical. Do you have a maybe comment on how you would expect things to change depending on the initial topology of the field, keeping beta constant?
So we actually kept beta constant. I came up with the B field initialization such that it's close to being vertical, but at the same time, it's also beta is around constant over a wide dynamic range. Are you asking about what if it changes to toroidal?
Yeah, exactly.
Okay.
For example.
Yeah, I don't think we have explored that idea yet. So I don't think I have a clear answer to that yet, but yeah, I think it would be interesting actually. Yeah.
Any other comments, questions? Yeah, please.
Yeah, so in this snapshot it looks quite a symmetry between north and south, and it's just not clear to me whether it is expected theoretically.
So I didn't really get to, because I didn't have enough time, so I didn't even really get to what is the characteristic of this feedback that we're seeing. But actually, the feedback that we're seeing in this non-spinning black hole case, it's coming from convection. And this is just one snapshot of the convection that we are seeing, but actually we find that it happens around the midplane at random angles all the time. So here we're seeing it's like pointing more towards the south pole, but at other times we find it at closer to North Pole. So if you take the time average of where this feedback is happening, it's actually more concentrated around the middle. Yeah.
Okay, let's thank Hyerin again.
Okay. So, hello everyone. My name is Franz Bauer. I'm from Universidad Católica in Chile, and I'm here to sort of promote and also get feedback from the community in general for the ALeRCE broker. So ALeRCE is the automatic learning for rapid classification of events, and we're one of the 7 selected brokers for LSST. And we've been actually working to, I guess, evaluate and classify the alerts from ZTF and also ALeRCE, and so we're sort of doing precursor stuff in anticipation for LSST. This is a huge collaboration. I just show a couple pictures of our collaboration meetings, and the PIs are Francisco Foster and Guille Cabrera Vives. So the motivation here is, the big elephant in the community, the LSST. And so I'm not going to go into too much detail about the properties of LSST, but just to sort of highlight that a given visit, which will be between 15 and 30 seconds, will produce something like 11,000 alerts. Most of those will be persistent objects, and we'll have a fair amount of bogus objects, some lots of solar system objects, and maybe some transients in AGN. And so we want to try and filter those out for your different science cases. So you might be interested in the solar system, you might be interested in the supernova or the tidal disruption events or some weird thing that is a small fraction of that. And the idea is how do we actually find these events so that we can go follow them up and you can do your science, right? So we're trying to enable science. We have these input telescopes. LSST is one and is sort of the main principal motivation, but there are others, space telescopes or gamma ray observatories or even gravitational wave detectors. And these things are going to produce alerts, and the idea is that we have some system of community brokers which can receive those things, classify them, try and filter out the junk you don't want to waste your time with, and then send these things through various either downstream brokers or target object managers to be observed, right, with whatever favorite instrument you have. And then, of course, the community will assess all of that, and then, of course, that will then feed back into this process. And this is the sort of time domain ecosystem, right, that we're trying to build and develop. And it's very complex. These are the various products that these brokers are trying to provide, right? And it's not negligible. There's lots and lots going on here. I'm not going to talk about most of this, but just to know that we are working on that. So I'm going to talk mostly about the things I'm kind of more involved with. The idea here is we have input data right now from ZTF. This is in the form of image stamps. So we have a science image, a reference image, and a difference image, and there you see the transient there. And then over time, that builds up. Right, and so you have image stamps, which give you some context. Then you have, photometry. You make a light curve from that, and so that's all fine. These are from the difference images. Typically, it's going to be a 5 sigma level sort of a detection. Then you might also have, if you want to go back, you need precursor data. So you might go back to the data releases or the science images and try and see what was going on beforehand. Ideally, you would want to do force photometry of that, right? And so then you would look at the difference image and just go through all of them and stack them. Okay, and then you might also want to include some kind of contextual information, say the host galaxy, the offset, et cetera, from deeper imaging, and so archival imaging. You might also want to do cross-matching with various multi-wavelength catalogs. So that's all the things we provide and sort of as our input. And so then we want to classify these objects. Okay, and so one of the things we wanted to try and do was to see how fast we could do that. And so we developed something called a stamp classifier. So based on the first stamp that comes in, it's an alert. We try to identify what it is instantly with one detection. And so we have in here a convolutional neural network that throws in these data points and then gives a prediction in the end. And we have 5 classes between bogus, asteroid, variable star, supernova, and AGN. You can see we do pretty well in the true label versus the predicted label. So we're getting a pretty high fraction, although it should be noted that the bogus is a huge amount of sources. So even 2% of the bogus might contaminate other things. And so that's been in production for many years now, and I'll mention some of the results from that, but we're also working on doing a multi-scale to build this out to scale, because one of the points is that the LSST is going to deliver a tiny little stamp of 6 arc seconds, and that's not going to have the broad context. And so if we can do a multi-scale and get the broader context, we may be able to do better. Also looking at a multi-epoch and multi-filter stamp classifier to build up statistics. Obviously, if you detect something in 2 images, it's no longer bogus, right? So you minimize the classes here. And then also we're looking at adding fast Fourier transform, which is a way of removing satellite. Basically, you have rotating satellites, and they show up as sort of these pearl necklace, and they can contaminate your stream as well. We have this thing called the ALeRCE Supernova Hunter, and here you show this is the ZTF detections for one night, and we can go and evaluate them, and you can go through and sort of see all of the various information and detect whether it's a candidate supernova or not. This is delivered. This is a score which is given by our classifier. So we could just cut it, or we could vet it and kind of select it. And so that we build up, and then we send this to the Transig name server for detections each night. And so you can actually see here we are, ALeRCE. We're working on the ZTF data along with, ZTF also has a bot that will do this. And so we're pretty competitive with ZTF, right? We're reporting half of the alerts, and we could do better. In terms of the spectral classification, we don't have any resources to spectrally classify them, but the community does, and so you can see, a decent amount of our sources are getting classified. And so what does that look like? So from something like 45,000 ZTF reports, and we estimate there's something like 5,000 that haven't even been reported yet. They're just sitting in the data. You can see that the vast majority of the objects we classify are supernova. We have a sort of contamination rate of about 2%. And then we also provide firm hosts from a code we call Delight. We're the only broker to be providing hosts with any reliability. You can see down here, we also started to classify TDEs. And in fact, about 28% of all the TDEs reported to date were reported by us. We didn't know they were TDE, but we reported them as a transient. Okay, and so there's still a lot that we can do here, room for improvement in terms of speed, completeness, purity, and so we're kind of working towards that. We also have a classifier based on the light curves. So basically we have 5 or 6 detected points, and then we try and classify it. And we use contextual information as well as the light curves. And we have a much more complex taxonomy here that we're trying to classify. And so in general, we have a lot of different features, many more than typically was used in the past. So we have something like 174 features, and we're using a random forest algorithm at the moment, which seems to outperform all the others that we've tried. And we have a pretty good confusion matrix overall, so taking this light curve and then just trying to figure out what types of objects they are, compared to say our stamp classifier, which is much more minimal in its taxonomy. We've just recently added the TDEs, and we're doing pretty well with those, although it's a limited set of objects to train on. This is something by Manuel Prevez in preparation. In terms of, we also matched up with the hosts, and so this is work by one of my students. So we have the host from Delight. We have the LC classifier has something like 30,000 overall objects. We can reject about something like 8,000 because they're not actually supernova. And in the end, we have a sample of 24,000 supernova. And the idea is to actually try and use more information about the hosts. And ideally, if we can recover photoz's, this will produce a much better sample. So this is what is spectroscopically classified. This is the host information in terms of specific star formation rate. This is the peak magnitude, absolute peak magnitude once you know the redshift. And you can see that the type 1s, type 2s, the 1BCs, they all kind of separate out pretty nicely in this space, whereas this is what we have from our classifier now. So we get the type 1s decently, but we see an overabundance of type 1BCs, which we need to fix, right? And so that's the idea behind using this host information to do that. Right, so basically we have too few supernova 1As at the moment. We have too many 1BCs, a few too many type 2s and superluminous supernova. And so we're trying to work out the kinks in the light curve classifier from that. So again, still room for improvements. We are also working on a multi-stream processor, so inputting both ZTF and ALeRCE and ATLAS at the same time. This, of course, is ideally pushing towards having LSST with a bunch of different other streams filling in and trying to classify those objects. And so we're trying to sort of develop this in a cross-platform sort of way. And so at the moment, like we have, ATLAS is giving us points here, and ZTF is giving us points here, and we can put them together to have a better estimate of this sample. We're also working with a mock data set of LSST, and we're doing pretty well in terms of this has a much broader taxonomy, and this is our confusion matrix from the light curves from this mock data set. So we're doing pretty well, and we're kind of building up to actually accept all of these alerts every 30 seconds. This requires a change in our database, so we're moving towards a MongoDB sort of non-relational database. And we have tons and tons of things that we need to do, or that we want to do, from an infrastructure side, from a machine learning side, from an astronomy side. And so, I would look forward to conversing with you guys about what your needs are, how you think we could improve things. I'm going to be here for the next 3 weeks. I'm visiting Igor, and so I don't need to necessarily have all your questions now, but feel free to come up to me and ask me things later. Thanks.
But frankly, I would subscribe to one category in your chart, which is bogus, because that may represent new sources that we haven't seen before.
Yeah.
So what do you do with those?
At the moment, we don't do anything.
You just
Yeah, but you can look and find them and go in. Yeah. But that's really the needle in a stack of needles that you want to find.
But that's the opportunity to see something that was never recognized because of a large flow of data.
Potentially.
Yeah.
Yeah.
Okay, comments, questions?
Satisfied everyone.
Yeah, it looks pretty good. Thank you.
Okay, thanks.
All right, can you hear me well? All right, so I'm Daichi Hiramatsu, a postdoc here. I'm in P317, so if you want to chat anytime, just come visit. And I'll be talking about one interesting supernova, like just one of many ZTF discoveries that Franz just mentioned. And then it's an energetic interacting supernova, which I'll explain, and in a complex circumstellar environment. So let's just I'd like to introduce what interacting supernovae are. So these are classified as type 2N. So I'll just call them like SNE2N. And then type 2 means they are hydrogen rich. So you see hydrogen lines in the spectra, and then N stands for nano lines. So you see narrow hydrogen emission lines in their spectra. And then this is how they are classified, and then names as type 2N. And the basic physics picture behind these spectral features is that you have this supernova ejector interacting with the circumstellar environment. So these circumstellar environment came from mass loss activities prior to the explosions. And then now the supernova ejector moving faster than these CSM are interacting with this CSM. And then it is this shock interaction that we see as these spectral features. So you see that really narrow regions in between forward shock and reverse shock, this thing, like really narrow region. So you don't see much of the supernova ejector that is below the photosphere formed at this shock interaction. But what's interesting here is that this CSM interaction traces the mass loss history in reverse. So it interacts with the most recent CSM formed, and then as it moves outwards, it interacts with the CSM that was ejected way before. So this kind of traces the CSM history. So that's really the interesting part of these type 2N supernovae, that you can actually learn the massive star activities prior to the explosion. So if you look at their light curves, so these are the light curves of these type 2N supernovae, they span like one wide range of parameter space. So in luminosity, they span like 5 magnitudes, and then the time scale is tens to hundreds of days. So you see such heterogeneity here, and then that likely reflects the CSM diversity you see in these massive stars. So one interesting case is this SN2009 IP, where you see really long precursors. So these precursors are not actual explosion, but this is the mass loss activities from the massive stars that you see as outbursts. And then at some time later, you see actual explosion that interacts with the CSM created in these precursors. So the big question here is that can we draw a consistent picture here from the precursors to the interacting supernovae? And then to make these precursors and supernovae, what are the progenitor channels? Are these luminous blue variables in outbursts, or extreme red supergiants, supersymptotic giant branch stars, or massive binaries? Anything that you can think of that could make these kind of environment. And then so now I'd like to jump on this particular supernova called 2021 QQP. So it's a type 2N supernova. It's an interacting supernova which shows multi-peaks. So here you see the light curves in some several filters, and then you see this main peak, and then about a year later you see this second peak. So this is a really complex light curves. And then if you so the sharp multi-peak light curve. So this is really the characteristics of this supernova. And then if you look at the colors, in this case G minus R, which essentially tracks the temperature evolution of this supernova, because as the temperature increases, the color becomes bluer. And then you see these bluer peaks at the light curve peaks. So it's likely indicating at the peaks, the temperature gets higher and higher, which likely suggests more intense CSM interaction that you're seeing here. And then in this case, if you go back after the fact, you see these light curves. You see this gradual rise in the light curve for over a year. So this is the precursor phase. So this is the part we think happened before the supernova explosion. And then this is coming from the mass loss activities of the massive stars. So, this is a really long duration transient spanning about 1,000 days, and then going through different phases. So this is an interesting supernova. And if you compare this particular one, which plotted as black points here, to a huge sample of type 2N supernovae coming from ZTF, you can see this is a really unique guy. It got this really long precursor and sharp peak, and then came back again. And it might have been rising before our observation stopped. So we we've taken additional data, but it's still under progress. It needs to be analyzed, but what we find there will have some implications to our conclusions that I make in a minute. And so, as I said, it's a unique amount sample. It's a cool guy. And then if you look at the spectra, as I said, you see now hydrogen emission lines like H alpha and H beta. And then these first spectra are taken during the first peak in the light curve. And then these four are taken during the second peak of the light curve. And I'm not getting into the details, but you actually see the stronger line emissions at the light curve peaks. So again, it's likely indicating more intense CSM interaction during the peaks. And then if you look at the line profiles of these H alpha and H beta, you can actually deduce some kinematics about like the velocity information of the, this CSM interaction shell, which I just put it as SNCSM, which is like, evolving from 8,500 kilometers per second to 5,600 kilometers per second from the first peak to the second peak. And then you can also get some estimates on the CSM velocity. So that's the velocity of mass ejected prior to the explosion, which is from like, 1,300 to 2,500 kilometers per second from the first peak to the second peak. So this is the velocity evolution for the CSM shell, and then also the unshocked CSM. And then, so since this is a really complex light curve, we kind of have to come up with the flexible analytical model that we can use to extract the physical information of this supernova. So here we use luminosity and velocity evolution as inputs, and then the output is going to be CSM density and then the mass loss history. So here we assume the observed luminosity is plotted as these black lines, and then we assume that the emission is dominantly powered by this CSM interaction. So the observed luminosity is the sum of the luminosity of the forward shock and then that of reverse shock. And then we value the explosion energies of the supernova, and then just plot the reverse shock against the observed luminosity. And then if the explosion energy is too low, in this case like these blue lines, the reverse shock luminosity becomes greater than the observed luminosity. So that is unphysical. And then in that case, the forward shock becomes negative just by construction of this model framework. So in that way, like, you can find a reasonable parameter space, or like the allowed parameter space for the explosion energy and then the ejected mass of the supernova. And then you can see that also in the velocity evolution, so these black points, the shell velocity, so this is the shell of the interaction that's happening between supernova and then the CSM. If the explosion energy is too low, this shell velocity decreases like too quickly compared to the observations. So this way you can also rule out some parameter space. And then, like as I said, the lower explosion energy and the ejector mass results in higher reverse shock luminosity and vice versa. This is because the deceleration is more efficient if your supernova explosion energy is small. So by doing the parameters, survey of the parameter space for explosion energy and then the supernova ejector mass, you can reconstruct this density distribution. So this is the CSM density distribution as a function of radius. And then, so as you kind of expected from the light curves, you see two sharp peaks. So this one corresponds to the first peak in the light curve, and then this one corresponds to the second peak. And then you can convert this to the mass loss history of the progenitor as a function of time to supernova, so time to the explosion. So you see a huge spike in the mass loss, like up to 10 solar masses per year, about a year before the explosion, and then another one about like 2 years before the explosion. So this way you can constrain the total CSM mass to be like 2 to 4 solar masses, which were likely produced in the precursor phase. And then the supernova eject a mass range of 5 to 30 solar masses within the explosion energy of 3 to 10 times 10 to 51 arc. So usual explosion energy for supernovae is about 10 to 51 arc. So this is about a few or maybe about an order of magnitude higher than typical supernova. And then given this information, you can say maybe the progenitor was the luminous blue body in outburst phase, or maybe really extreme pulsation pair instability supernova, which you'd expect from really high mass end of massive stars within like 110 to 140 solar masses at zero-age main sequence, or maybe an extreme binary like wallflower plus compact object, either neutron star or black hole, that they merge. So this might cause this quasi-periodic evolution, which we might be seeing here, because like each close encounter, it ejects some kind of mass, which results in this mass loss peak in the CSM mass loss history. So there are a bunch of possibilities. So that, as I mentioned, our observations are still going. And then if we see a third peak somewhere here, that might suggest this mass loss is more like periodic. So in that case, the binary progenitor system might make sense. So the observations are still going. So we'll see more in the near future. So this is just summary, as I mentioned, for the future remarks. We are still observing this guy and then really curious to see what conclusions we can make from that. And then another one is that for this kind of supernova, like 21 QQP like precursors with LSST, we're going to increase the sample size by, roughly 2 orders of magnitude. So using this framework, I'll be really curious to see the mass loss history and then the supernova properties as population. So that's it, and thanks for listening.
Actually, that is fascinating, but you get a projection every year of roughly a solar mass or 2 solar masses, and the question is how long did it continue every year, because soon enough, within 30 years, you'll consume all the mass of the progenitor or whatever, right? So then why does it happen in the last few decades of the star, like this ejection of a solar mass per year?
So yeah, that's the really tricky part that I don't have a clear answer to. And then, I've asked the same question to Morgan, actually. If we could actually model this kind of system, and as you mentioned, what the lifetime would be, and then how much, what's the time scale that we can see. So I think that's the next step on, actually doing the dynamics and then see, whatever I said actually makes sense or not.
So if it's a binary, something should happen to the star that makes it puffed up, and then you start ejecting for 30 years at the end.
Right, something like that. So it might go through common envelope phase, which puffs up, and then, maybe with some clever tricks, you can merge, the system within common envelope, and then that might mimic, what we see here.
Because if we understand that, maybe we can figure out which star is about to explode in the Milky Way.
Yes. Yeah. So I think.
30 years.
Yeah, I think that's a really interesting point, and then which is kind of related to my last point here. So based on the precursor activities, can we say, roughly when this star is going to explode?
Go ahead.
Yeah. There is one such star that might explode, this Accretion,
Right.
that had this outburst about 100 years ago. And I guess it was this order of magnitude mass loss, maybe a little less. But it still hasn't exploded after a century.
Well,
So-
wait a decade.
Do you think that there might be cases like this? But because normally in your model, it should be manifested by the outburst much later in the light curve, I don't know, maybe a year after. Or you just stop observing supernova after a year, so you will not find out about it.
Yeah. So in a decade, for this supernova, if we could actually detect, up to that faintness, we might see a bump in the light curve, which corresponds to whatever the mass ejected, century ago or something.
Okay.
So we don't have that much of information at the moment. But like, we are trying to extend this time as long as possible. And then with LSSD, as I mentioned, it's going to be deeper than the current survey. So we might have some hope.
So Daichi, if you had to make a bet about when Eta Carina will explode, do you think it will happen in your lifetime?
Hopefully so. Yeah.
Okay, with that happy note. Okay,